Have you ever tried to use your favorite advanced large language model, think GPT-5 or something similar, on a truly enormous document,
Oh, yeah.
like a multi-volume legal report or a full corporate code base, maybe even an entire series of books?
I think we've all been there. You have this promise of limitless knowledge and insight, and then you just hit the context wall.
Exactly. It feels like you're holding a rocket ship and then you suddenly run out of fuel.
Mm-hmm.
Even the most powerful models, they just have a hard limit. You can only shove so many tokens in before the system gives you the digital equivalent of a hard stop.
Right. And that hard capacity limit, which for some of these frontier models might be, what, around 272,000 tokens? That's just the most obvious problem.
Tip of the iceberg.
Exactly. What the research into these new recursive language models, or RLMs, really brings to light are two critical issues. First, that hard limit, yes. But second, there's this more insidious problem called context rot.
Context rot. I love that term. So why does the context dot rot?
Well, it's really about how the underlying transformer architecture works. Every time the model processes a new token, its attention mechanism has to look back at all the previous tokens. So when the sequence gets really, really long, the attention weights just get spread too thin. The model starts struggling to, effectively retrieve or maintain relevance for the tokens that showed up way at the beginning.
So it's like trying to keep, 200,000 tabs open in your brain at the same time.
That's a perfect analogy. The crucial detail you read on tab number 1 gets completely buried, effectively forgotten, by the time you open tab 272,000.
So we have these incredibly capable models that can reason brilliantly, but they're physically bottlenecked by the sheer volume of data. And their performance starts to degrade even before they hit that hard limit if the task is complex enough.
Precisely. We saw in the source material that on really complex reasoning tasks, like one-oolong pairs, the performance just degrades catastrophically as the context gets longer.
The model loses focus.
It loses focus, and it loses the ability to aggregate details that are far apart. But here's the breakthrough we're diving into today. This recursive language model strategy.
Right.
This approach is letting LLMs handle inputs that are, get this, 2 orders of magnitude beyond the base model's capacity.
2 orders of magnitude, so we're talking.
We are talking up to 10 million tokens and beyond, and at the same time, it's skyrocketing the quality on those complex, long-horizon tasks.
So the core claim here is huge. It's unbounded input length and better reasoning quality. What's the secret sauce?
The secret sauce is actually, it's borrowed from decades of computer science, specifically the world of out-of-core algorithms.
Out-of-core algorithms.
Yeah, these were systems designed to manage enormous data sets that would never fit into a computer's main memory. They only used a small, fast slice of memory to process huge amounts of data.
So the RLM approach takes this idea.
It takes that idea and applies it to the prompt. It treats the long prompt not as tokens to be crammed into the neural network, but as a resource in an external environment.
Okay, so let's unpack this. If I can't fit the entire Encyclopedia Britannica into my brain, the RLM strategy says I shouldn't even try.
You got it.
I should treat the encyclopedia as an external resource, like a library.
Exactly. Think of the base LLM as having a small but extremely fast short-term memory. That's the context window. The entire prompt is the enormous external library.
So the LLM doesn't read the whole library at once.
No, it becomes a very smart librarian and researcher. It uses code to navigate the library and pull only the relevant snippets into its short-term memory just as needed.
But how does the LLM, which is, usually just dealing with text input and output, suddenly become a librarian running a search query?
It fundamentally changes its operating mode. So the RLM strategy doesn't feed the massive prompt directly into the transformer. Instead, it starts up a programming environment.
A programming environment.
Specifically, a Python readable print loop, or a REPL. The entire input prompt, let's call it $. It doesn't matter if it's 10,000 tokens or 10 million. It's loaded as one gigantic indexable variable inside this environment.
So the prompt becomes a static, massive data object that the LLM can manipulate using code. The LLM itself turns into a programmer.
That's the core architecture. The LLM writes Python code to interact with that variable $. It can write code to peek into it, to decompose it, search it with regex. It can observe the side effects of execution.
So it's no longer just reasoning over a continuous sequence of tokens.
Right. It's reasoning over its own code execution and the results that come back from the environment.
I see the language model part and the environment part. But where does the recursive layer come in? Couldn't we just write a simple script to search that huge variable dollars? Why do we need the full LLM to manage this?
That's a great question, and it really gets to the difference between simple retrieval and complex reasoning.
Okay.
If the task was just, find the word banana, a static script would be fine. But what if the task is find all references to agricultural exports in the 1890s in Chapter 7, and then cross-reference those against the trade agreements in Appendix B?
Ah, I see. That requires actual reasoning.
Contextual localized reasoning. So the RLM is encouraged to programmatically construct these subtasks like finding the exports in Chapter 7 and then invoke itself.
And it calls itself.
It makes a recursive sub-LLM call, an LLM query, over just that specific, small, and manageable snippet of the input variable dollars. It delegates localized reasoning to a fresh instance of the model with a completely clean context window.
This sounds way more powerful than, the older context condensation methods. I remember systems that just tried to constantly summarize what they'd already seen.
And that's the key technical advantage. Context condensation, it inherently assumes you can safely compress or forget details.
Which you can't always do.
For dense reasoning tasks, you absolutely cannot afford to lose those nuanced details. RLMs allow for dense access to the entire prompt length through programmatic search. It ensures critical pieces are only lost if the model explicitly decides, via code, not to retrieve them.
Let's try to visualize this with the example from the source material. We have this impossibly long book, and the prompt asks us to list items made before the Great Catastrophe.
Okay, so the RLM doesn't try to read all 10 million tokens sequentially. It might first reason, okay, I need to find the catastrophe date, then search chapters before that date. So it writes some Python code, maybe something like sections to check, prompt.split, catastrophe markers, to break up the prompt variable $. Then it calls mquery, that recursive sub-LM on specific isolated chunks, to find answers like the silver flask or Herod's ring.
So the sub-LM acts as a localized reasoning engine. It doesn't have to worry about the other 9.9 million tokens at all.
Not at all. It just focuses on the 10,000 tokens it was handed. And the root RLM, the one operating in the REPL, it collects those localized findings and stitches them together into a final answer variable. The final output is a coherent aggregate answer based on all that dispersed reason information.
Okay, so this is where we see the results of this shift. How did this strategic move from token management to programmatic management actually perform? We had sources detailing evaluations across 4 different tasks using frontier models like GPT-5 and Qwen3-Coder.
The results were, well, they were simply dramatic, especially when pushing token counts way past the conventional working point.
And the highest scaling test was that BrowseCon Plus benchmark, right?
It was. This one requires reasoning over 1,000 documents, which translates to a context size between 6 million and 11 million tokens.
I have to stop you there. 11 million tokens. That's almost impossible to even visualize. What does that compare to?
That's roughly 15 to 20 full-length novels simultaneously. It is completely infeasible for any current base LLM.
And the results showed that.
They did. The base models, GPT-5 and Qwen3, they failed catastrophically. They scored 0.00% because they hit the context limit and couldn't even ingest the required data.
A hard zero.
A hard zero. Now, contrast that with the RLM strategy using GPT-5. It achieved a 91.33% performance score.
Wow.
So this isn't just a success in scaling input size, it's an operational triumph. And it also significantly outperformed traditional long context baselines like summarization agents by over 29%.
So scaling to 11 million tokens with over to 90% accuracy, that's a profound shift.
It really is.
So that addresses the scaling challenge. Now let's go back to the complexity story. You mentioned the base models fail on highly complex reasoning tasks, even within their own context window. What did the RLMs do there?
Right, so we saw 3 complexity levels tested. SNIH, which is constant complexity, just a simple search. Then oolong, which is linear complexity requiring aggregation, and then oolong pairs,
which is quadratic complexity.
Quadratic complexity and highly information dense.
Can you define quadratic complexity for us in practical terms? What does that mean for a model?
So quadratic complexity, when you apply it to reasoning, means the workload just explodes exponentially. If you have n pieces of information, the task requires n squared operations.
Okay.
For the LLM, it means for every new piece of information it processes, it has to check it against all the previous pieces of information to find the right pairing or relationship.
So that's why an LLM couldn't reliably compare, say, 5 massive legal contracts at once.
Exactly. It was choking on the complexity of relating every clause in one document to every clause in the others. It's not just the sheer word count.
That makes perfect sense. So how did the RLMs tackle this impossible quadratic task?
Well, the base GPT-5, it essentially failed on oolong pairs. It scored less than 0.1% F1. It just couldn't manage the dense pairwise relationships.
Less than a tenth of a percent.
Almost nothing. Yet RLM with GPT-5 achieved a 58.00% F1 score.
58% compared to almost nothing. That's not just a linear improvement. That feels like an emergent capability.
Yeah.
It's allowing the model to solve a problem it was previously just incapable of solving.
Absolutely. The ability to programmatically decompose the input, delegate the task of finding pairings to these isolated fresh sub-LMs, and then aggregate the results back in the REPL environment, that's what unlocked that performance.
This system has two main components, right? The REPL environment for programmatic access and then the recursive subcalling capability. Which one is the real engine here?
That's a great question, and the ablation study gives us a really crucial insight.
What did they find?
They tested the RLM with the REPL interaction, but without any subcalls. And that model, it still scales beyond the hard context limit because the prompt is in the environment, not the context window.
So it's already better.
It performed significantly better than the base models on many tasks. For example, Qwen3-Coder on Code QA jumped from 20% accuracy to 66% just by using the REPL to search the code programmatically.
So the REPL environment alone solves the scaling problem by letting the model selectively view the input.
It solves the scaling problem, yes, but the recursive subcalling, that's what's crucial for solving the complexity problem. On oolong pairs, adding the recursive subcalls boosted performance by a factor of 10 to 59% over the REPL-only version.
So scaling requires selective retrieval.
Right. But dense reasoning requires localized, complex analysis, and that is the job of the fresh, small context sub-LM.
So what does this all mean for how these systems behave? Are they just following program steps, or are they showing some genuine intelligence in how they manage context?
What's really fascinating here is the evidence of emergent context management behavior. These are strategies the models developed without being explicitly trained for them.
Okay.
We saw 3 primary emergent patterns in how the RLMs process things in their trajectories.
Give me an example of this filtering behavior you mentioned.
So first, there's filtering. The RLM uses code execution, specifically regex queries, based on its prior knowledge, to quickly filter massive inputs. For a task with 8.3 million tokens, the RLM running GPT-5 was observed deciding, mid-process, that it only needed to search for keywords like festival or La Union to narrow the context instantly.
So it's not processing the whole thing.
It avoids processing everything by dynamically performing retrieval based on its own reasoning needs.
It's acting like a highly intelligent database administrator deciding the most efficient query path. What else did you see?
Second, answer verification. The RLMs would start up subsequent sub-LM calls with a small dedicated context just to verify the information they had already gathered.
So it's double-checking its own work.
It is, and it's an implicit strategy to avoid context rot. The verification step happens in a clean, small context subcall, which ensures the model isn't confused by irrelevant, distant tokens when it's confirming a finding.
That's a highly sophisticated error-checking process. And you mentioned how they handle massive outputs as well.
Right. If the answer itself is incredibly long, like a massive list of user ID pairings required in oolong pairs, the RLM stores the results of all its little sub-LM calls into those REPL variables.
Like a scratch pad.
Exactly. And then it stitches them together programmatically before delivering the final result. It completely bypasses the output token limit of the base model by using the external environment as its memory.
Okay, let's pivot to cost and behavior stability, because this sounds computationally intensive. If we're replacing one long query with hundreds of smaller recursive ones, aren't we just swapping context rot for an exploding API bill?
Surprisingly, the answer is often no, not at the median anyway. The average API costs for RLMs are often comparable to, or even cheaper than, the base models or standard summarization agents.
Cheaper.
Because compared to baselines that have to ingest the entire context, RLMs can be up to 3 times cheaper while performing better. They selectively view the context using code. They avoid paying for tokens they don't need to look at.
It's incredibly efficient.
However, and this is a critical caveat, the inference cost is high variance. It has a long-tailed cost distribution.
What does that mean in practice?
It means because the RLM is iteratively searching and reasoning and calling sub-LMs, complex tasks can lead to these long, expensive failure trajectories.
Can you give us an example of that kind of failure?
Yeah, we saw it clearly with Qwen3-Coder on the oolong pairs task. In one instance, the RLM just got stuck in a loop. It was observed repeating the same process 5 times in a row.
5 times.
5 times, iteratively trying to rechunk the data and call a sub-LM before finally giving up and outputting an incorrect answer.
So the stability of the model's programmatic decision-making becomes the new point of failure, not the context window size itself.
Precisely. And this highlights that while RLMs are a model-agnostic strategy, you can plug in GPT-5 or Qwen3, the models themselves behave very differently.
How so?
Qwen3-Coder was much more liberal with its subcalls than GPT-5 was. It got to the point where the researchers had to add an extra prompt warning specifically to discourage excessive recursion and force it to batch information more efficiently.
So if we connect this to the bigger picture, this isn't really about managing tokens in a neural network anymore, is it? It's about managing resources in a programmatic environment.
It's a fundamental shift in paradigm. I mean, we are now dealing with programmatic reasoning over massive data resources using code and recursive self-calls.
And this lets LLMs genuinely tackle these real-world, long-horizon tasks.
Yes, tasks involving documents that are millions of tokens long, and they can do it efficiently and reliably. This transforms how we approach everything from debugging vast code repositories to, full legal discovery.
The potential application is enormous. The ability to reliably reason over a massive code base or an entire contract portfolio, that's truly game-changing.
It absolutely is. And this brings up, I think, the ultimate provocative thought for the future.
Okay.
While RLMs show this stunning emergent performance using existing frontier models that were trained mostly for conversational text, we've already seen that their performance sometimes suffers. They make inefficient context management decisions like those repetitive subcalls or poor chunking.
They aren't natively trained to be efficient system administrators of a REPL environment.
Exactly. So what if models were explicitly trained from scratch to reason efficiently as RLMs? If you could train a model to maximize computational efficiency within this REPL environment, you could eliminate those expensive repetitive loops and optimize the whole decomposition process. That kind of specialized focused training could provide another massive axis of scale and efficiency for the next generation of LLM systems.